Recording is on. Okay, I'll share. My that. Okay. So already there. So let's go to the Moodle web page first. Attendance. Today is April. Yeah. So could you please take your attendance for those who are already there? Can anyone give me a feedback? Do you hear me? If you hear me, just reply on the chat or just give me a. Okay. Can you hear me? I just want to make sure you hear me. Okay. Yeah. Good. So people hear me, so I can start to conduct this afternoon session. I think just now our last sessions, due to some technical reasons, the line was very bad. But I think the problem was sort of like fixed. That happened because I am opening two devices. One is my laptop, the other one is my iPad. So because of that, my data doesn't support. So the sound is sort of like very lag. Now, if the effects is very lagging, please feedback to me and let me know so that we can try a way to overcome the problem. So people are still coming in. Now I see only 15 participants. So I think we have 20 something participants. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are only 15 participants. We should have about 38 participants. 16 now coming in, 17 coming in. So I'll wait for a while, doesn't matter. I suppose you also see my sharing screen, right? So you are supposed to see a QR code in front of your laptop. Just take a snapshot of the attendance. Later on, if I forgot, just remind me to show you the QR code again, in case there are people who have not attendance. Now, I think this is a learning process. I myself is also in the process of trying to familiarize myself with this online teaching. Either sometimes the line is slow, sometimes I get lost in my computer planner thing like that. But I think I'm getting used to it. I hope that you can also get used to this. That we can continue our learning on the line more easily later. We won't start so early because of this online thing is always very troublesome. So I'm still waiting. Anyone want to say anything to me? You can post your chat, you can post your on the chat so that I can respond to you if you don't want to speak out on your microphone. But it would be best if you can post your questions on the microphone. Instead of me speaking alone, I would be very happy to hear some response from the group as well. Okay, so maybe we can begin our lecture. I'll try to make my lecture to go as smooth as possible. See, it's sometimes very difficult for me to speak very naturally. If I'm in my class, I'll be able to speak, like dancing and acting, so that people would feel so bored. But if you're sitting in front of your laptop and no response is heard from you, then sometimes my performance is just go not very optimal. Anyway, we are going to continue our lecture on part 5. So if you go to the your where is it now? We go to the so we will continue to get to discuss on the item part 5. So you click on this, then you land on this and be not. So my lecture will be based on the on this part 5 book, which you can easily download. So it will be the same code as we have discussed in the last lecture, but we are going to finish this by today. So we assume that you can do this time stepping. Anyway, I assume that you have familiarized or you have already submitted an assignment on this time stepping. So my plan is not to continue on this part. You try to read this and try to understand this, and then to submit your assignment as already done. But just to remind you, this part on the time stepping that I discussed in the last few lecture, some corrections. I think the formula that is shown, formula number 5 and number 6, could be slightly different than the previous version. So this is a correct version now. Okay, so when you write your code to time step the velocity, you're supposed to use this formula and use this formula. Okay. So before I leave this part of time stepping, what I'm saying is that this is an example of solving the first order differential equations numerically. Okay, so this is how you do it now. You discretize the differential equation A equals into this form, so that you express V in terms of the previous V and the product of the acceleration function and delta t. So you know the function as delta t. So this is a code that will do this, right? So this is a code that will generate different values of t. Then you calculate the values of n or v at the present n, and it is the sum of the previous a plus the product of a at the present time multiplied with delta t. So this is the most important formula that I highlighted on the screen. Is just this formula, okay, equation number 6. So that's how you implement this equation number 6 into a very short and simple loop. Then you let the time to run from 0 to t last. Then you'll be able to obtain the function of v versus t. Then you display the function of v versus t. So in this way, you are actually calculating the values of v from the function of a. The function of a is already given, so you have defined the function of acceleration, and you derive the values of v from a, from this difference equation. So these equations, the result of v versus t is supposed to be the same as the values of v that is derived from here, right? So this function of v, if you plot it out, the shape of this function v and the values of the shape of the function v that you obtain here be the same. Okay, it's just that in this case, the values of v is obtained by time stepping the difference equations. In the function v is just calculated directly from the formula. Okay, so try to see the difference between this part of the code and this part of the code. So this is more complicated. This part of the code is more complicated because you don't have a function for v, but you derive the numerical behaviors of v from the function of a. Okay, so that is what I want to tell you. Any questions? Could you please state so that I can clarify anything that is not clear to you before we move to the next part. So everyone seems to be very quiet, and I seems like talking to the air. Okay, someone is speaking? No? Okay, so the plan today is to go on a SciSpy. Okay, this is SciSpy is what we are going to talk about. So I have cut out this SciSpy in a independent code. So I'm going to use my versions of SciSpy code. Okay. So let me close this. And let me close this. Close this. Okay. So we are going to talk about the SciSpy code. So what is the SciSpy code? So SciSpy is a package in Python that allows you to perform many different types of numerical tasks. Now, what kind of numerical tasks are you talking about here? For example, if you have a function and you want to integrate the functions from, say, x1 to x2, or if you have a function, if you want to differentiate the function, okay? So after you have differentiated function, you want to plot out the differentiation of function versus x. The other thing would be to perform an optimization. Right? So you have to fit the data against some function, then you will do it using the SciSpy. So I think it would be better look at some specific example in this SciSpy package. Okay, so what we are doing, the SciSpy package is a very SciSpy package is kind of a large package. We're going to look at particularly a SciSpy optimized package. Now it's called optimized because there is a built-in function in the SciSpy code that allows some kind of optimization to be happening in order to obtain the best solution. Now I'll try to explain to you later on what is the optimization doing. Okay? But the best way to explain to you the functions of an optimization is by looking at a sample. So to this end, we are going to talk about fitting a data against a function. Now, do you know what is meant by saying fitting data to scientific model? Now, when you say scientific models here refers to function of mathematics. So you have two things. One is the data, the other one is a function. I'll give you an example. I have some example here called data fitting. So this is the general idea of curve fitting. Now, what you mean by curve fitting is this. First of all, you have some kind of data. Now, this is a very common situation where you have seen in a lab. Right? So I have a set of data, x1, x2, x3, and many data. So this is data. Now, in your case, you try to fit the data onto a model. In this case, the model is a linear function, which is y equals mx plus c. So here, y equals mx plus c is the model. So in this model, you have two parameters, which is unknown yet, which is m and c. So what you want to do is to try to adjust the values of the parameter m and c in your model such that the graph of the function will go to all these data points as best as it can. Right? So imagine if you put in the wrong values of m and c, then the function of y equals mx plus c will go through some line, it will still define a line, but the line for the wrong M and C would not go through the data points as between. So what are the best values of M and C? So this is your purpose. You want to find your best fit parameter for this model onto the data point. Right? So you have a data point, which is all fixed that you measure for experiment, and then you are given some model, and your job is to find the parameter, the best parameter in the model, such that your function fits on the data as best as you can. Right? So this is an optimization problem. Now, what I mean by optimization problem is that if you define your M, well, if you put in the values of M and C differently at a different value, then the line would deviate from the best line, right? So you have to constantly adjust M and C a little bit by little bit. And when after you have adjusted the values of M and C, then you compare the functions of Y with the data point and try to calculate the discrepancy between the data point and the line. So if the line is too much off from all these data points, then the discrepancy between the data point and the line will become larger. Right? So imagine that if you adjust M and C, there will be a time when if M and C are the best fit value, then the discrepancy between the function Y, which is straight line, and all the data points will have the minimum amount of discrepancy. So that is the solution you want to find. So the optimization process is a process of constantly adjusting the values of M and C such that the discrepancy between the data point and the function is minimum. Right? So the optimization here is actually a minimization problem. It's trying to minimize the discrepancy between the data point and the functions. Right? So when you have found the best value, then you have found it. So this is what we want to find. Right? So remember in your first year lab or in your second year lab, you do this so-called least square method. Right? So if you go to second year lab, I think first year lab also you have this. So you try to find out what is the best slope and the best values of the intersections of Y. So you draw a line and then you try to adjust your ruler. Then you try to draw the best line. Right? So that is a optimization done by you yourself manually. But in the Python, it has an automatic procedure that will try to adjust the values of M and C using some smart method to get the best values of M and C. That's why we call this finding the best parameter of a model against all the data point is an line fitting process. And this line fitting process is an example of optimization. I'll give you an example. So, so you see on my screen, we talk about a Gaussian function. A Gaussian function is a Gaussian function. So, for example, if you obtain an experiment, x and y value. So this is the x coordinate, and this is y coordinate, and you have this x1, y1, x2, y2. All these data points are distributed, and you sort of look at it, and then you say, oh, these data points should be fitted on a Gaussian function. So this is a Gaussian function. Y equals to a e power minus x minus b squared is what we call a Gaussian function. So you assume that if you can adjust the values of a and b nicely, then the function defined by this Gaussian function should go through the data point very beautifully. If you don't know what is the best value of a and b, and you simply plot a and b, or you simply use a set of values of a and b, then which is described by this y will not go through all these points. So if you have found a and b as the best value, then that's what you find. You should find a very nice and beautiful function that goes through most of these data points. You don't need to go to all these data points one by one, but this should represent the best fit function with the best fit parameter a and b. So your purpose is this. If I give you a set of data points and give you a functions, your job is to try to find me the best fit parameters. Okay, so that's it. What we're going to do with the SciSpy function we're going to talk about today. Another example, right? So if you have a set of data points that looks like this, and then you are told that this data point can be fitted on a polynomial of a0 plus a1 plus a2 plus a3 with sort of like expression. So what is the values of a0, a1, a2, a3, such that the polynomial will pass through all these data points as much as it possibly can? So this is again an optimization problem. It could be easily done by using the SciPy optimized curve fit function. Okay, so this is the agenda. Okay, I'll wait for your response. Anyone want to ask anything? Ask now. Want to ask anything? Fine. So in the process of optimizations, you have to provide the three information. First of all, you have to provide what is the function, right? So you have to tell what is the function you want to fit, and of course you have to provide the set of x data and y data. Then the code of this SciPy will be able to give you the best fit parameter you are looking for. Okay? Now this is an example, very simple example. So given x data, yeah. Any questions? I'm listening for someone. Yep. Okay. If there's no I'll continue with this. So here we're given an example of x and y data. So you have 1, 2, 3, 4, 5, 6 data point, 6 data point for x and 6 corresponding data point for y. So you are given this function f equals to a second order polynomial. I think there's some error here that needs to be corrected. It should be x power 2 b of ax power 2 plus bx plus c. So this is your model that you want to fit again the data of x data and y data. So what is the best fit parameter of a, b, and c? So this is your questions. Now when that is done by, yeah. Someone saying something? I stop for you. I had no forgotten to switch off your mic. But let's proceed. The SciPy not only will provide you with the best values of A, B, and C, it will also print you the error. Like when you fit the data, the function would contain some error. Right? So when you fit this data against a parameter, against a function, the values of the best fit parameter should also contain some error. So SciPy will also of the values of A, B. What to do is first let us know the data and the five the fitting is done, the values of A, B, and C would be calculated. Once we have calculated the values of A, E, and C, and the calculated value. Okay. So the line would get like I'll take see monitor. So once the values of A, B, and C is calculated, what we want is to plot the functions using these values of A, B, C. Then we will want to overlap the functions onto the XY plot. Now, if the functions is fitted correctly, you will see that the functions and the data point should each other nicely. So this is the code. It's very simple code, right? So first of all, you import SciPy, then you import the optimized package from SciPy. Then you the graph. Then the functions you want to fit This is the key, right? So you just have to know how to use this optimized curve fit. So the optimized curve fit is an object under the SciSpy. So you call out the optimized curve fit object from SciSpy. Then this optimized curve fit SciSpy emits 3 arguments. The first argument is a function you want to fit. Then you have to provide the x data and y data. So in this case, the functions to fit is a function of x and also 3 parameters. So x is understood to be the variables that corresponds to your x. Okay, so you have to call this x. Then ABC is the data that we will try to find for you. Okay, so let's just try to do this one by one. You can follow along if you want to. I'll try to see if I can imitate all these things from scratch. Give me 5 minutes to produce the code that is being specified here, so that you know instead of click on this, you can follow along how we do this. So first of all, we import SciSpy. Then we import SciSpy optimize. Then I enter. See, okay, so there's no problem with that. Then from there, from pilot, I would also then import everything. So I have problem to import. Okay, so now I have to paste the data. Okay, so this is the data, x data and y data. So before I proceed on, I would really want to see how this x data looks like and y data. So it's a set of data that looks like this. So this should be points. So I should plot points. Just a dot will do. So I have all these data points that's shown like this. Okay. So now I see my point, my data point. So what I'm going to do next is to use the SciSpy. So I have to look at my question. My question is to fit this data onto a polynomial function, ax squared plus bx plus c. So this is what I do. Ax, so I define my function, f. The function should emit a and the function of x. So and then a, b, and c. Right? So a and b, and c are the number that I have to supply. And then okay, so I have to have a double column here. Then the function is defined as a multiplied with x power 2 plus b multiplied with x power 1 plus c. So this is what I'm going to return. Okay. So to make sure that I got things correct, I'll just print out some number. Say f with values of 1, a, 1, b, 3, c is say 7. So I press button, I want to see a number. Yes, I see a number. So that means my definition of the function f is correctly done. So now it comes to this. I need to call in SciSpy. And then I have to call in SciSpy optimization fit. I forgot the name. So optimize the fit. And I apply the functions to be defined, to be fitted. So in this case, it's a function f, and the x data is defined here. It's a set of 6 number, and y data is a set of 6 number. Now, mind you, in this case, the x data is in calculus called the independent variable, whereas y is called the dependent variable, right? So you have to supply. Normally, the independent variable are a variable that you can control, whereas y data is the dependent variable, where its value is depend on x as well as a function. So when I press a button, if this thing works, I should see no error. Okay, so it print up an number, an arrow, an array. So this is the result of an array. So what I'm looking for is the best fit values. So the best fit values is this array. The result is an optimized. So the result is printed up. And that is, so let me try to understand the result. Okay, so you plug in the 5 fit data, and the result is an array. This is the first array. And then this is the second array. Now, try to understand what is meant here, okay? Now, the optimized curve will provide you with the best fit parameter. Now, what is your best fit parameter? In this case, x, which appear in the first instance, is the, whereas a, b, and c here is the parameter you want to find. So the first array, the first array, refer to the values of a, b, and c. Right? A appear first, then b, then c. Now, what is this? The second array, I think, if I'm not mistaken, it refers to the error. The error in A, B, and C. Dimensional error that describes, well, there are many ways to describe the error. So I think this is the error matrix, okay, that is relevant for A, B, and C. But for our purpose, we don't normally concern too much about the error. What we concern is the best fit value for A, B, and C. So we call this, well, call it best fit parameter. The SP stands for best fit parameter. So let me print out the best fit parameter. The best fit parameter is this, and I want to know what is the shape. So the shape of the best fit parameter, best fit shape, shape, the shape of best fit parameter is an array. No, something is not right here. The SP is this one. Print out best fit parameter. So it looks like it's an array 1, 2, 3. So let me array 1, array 2, array 3. Okay, so this, according to my understanding, refers to the ABC. So let me call out the first element in the array. The first element is not being called out correctly, so I'm a bit confused. So let me try to come back to here. So the result is print out. I always get things confused because what I want is to look at the 0th element, not at the first element. Okay, so now there's no error. No, still some error. Print BFP. So maybe I should not try to guess here. Let me try to add the solutions. Okay. The result is an array with 2 elements. Okay, so it means BFP, which is obtained from the fitting, is an result with 2 elements. Okay, the first element is a list containing of B and C. Yeah, this is what I said just now is correct. So the second element in the output is 3 by 3 array. So it is a covariant matrix of error. So what we are concerned, let me try to add one here. So B best fit parameter. So this is result. So this is the A, best fit value A, this is best fit value B, best fit value C. Whereas this 3 by 3 matrix is what we call the matrix, coefficient matrix. So the coefficient matrix have 3 by 3 element. So this element 1, 1 is the error corresponds to A, whereas the 2, 2 element in the error matrix corresponds to the error for B, whereas the 3, 3 element in the matrix of this error matrix corresponds to C. So we have performed optimization here. The values of A, B, C has been obtained. The values of A is this 1.044 with the error of minus 0.06, whereas the best value for B is minus 0.18 with the error of 0.03. And then this is the values of C, which is 0.08 with an error of 0.03. 0 for 1. Okay, let me repeat again. The error for this, actually this one. I just like to make a look. This is A. This is a error in A, and this is an error in B, and C is this, and this is an error in C. Okay. So now, in order to obtain the best for A, B, C, you have to the best values from the error from the output. So okay, let me try to see this. So this is the error. This is output. I'm coming here again. Now this is the BFP. The first element in BFP is this. Okay, so this should refer to the best values, which is this one. So best fit value is this, right? So the 0 element in the output contain the best values of A, B, C. So then what is A? So usually A is just equals, well, A best fit. We have A best fit is the first element in the BFP 0 array. Okay, so this refers to this. So I hope you understand what I say here. BFP is an output from the optimization curve fit, and output matrix of 2 elements. The first element, which is BFP 0, contain the best fit values of A, B, and C. Therefore, the best fit values of A is the 0th element in BFP, whereas the best fit value for B is a second element in BFP 0, and the best fit value for C is the third value. Okay? So ABS, BBS, and CBS. Right? So this is the best fit values for A, best fit value for B, and best fit value for C. So now I would like to do this. I would like to print up the functions of x as a function of x and ABS, BBS, CBS. So when I press the button, I'm not sure what I could get. I expect to see a printed out. ABC has been replaced by the value, so it doesn't allow me to do that. So because I have not supplied the values of x correctly, so I can't print out the functions. But what I can do is that I can print out the functions of f. So now I have obtained the best fit values of A, B, and C. So I will plot x data as usual and y data, right? And then this data I plot it as so this is original data. Now I want to plot. So this is the original data which is already plotted. Okay, so now how do I plot the functions? I want to plot these functions where I slot in the best values of A, B, and C. Okay, so let's see how we plot this function. First of all, I think it's quite easy. What you do is, let me try this. I have not tried this before. So let me generate the values. Let me generate the values of the function of f based on this data. Okay, so this I would say f A, B, comma, C, comma. Okay. So I'm going to take the values of this using for I in X data. Okay. So when I say for I in X data, X in X data. So when I do like this, the values of X would be taken out one by one from X data. But then I will also have to provide A with an replace the F and A in the function here by my best fit parameter A, B, F. Whereas B here, I'll replace it with by BBF. This will be CF. So when I print this, I will expect to see a list for X in X data.
The CBF.
Sorry?
F is not CBF.
It's not BR. Okay, fine. Thank you very much. BBR, CB, wait, CBF, CBF. Sorry, this one, for X, this one. Yeah. So I have now obtained a set of data. What is this? This is actually my functions of F evaluated at each values of X, where X is just the X data. And here I replace the A, B, and C with the best fit parameter. So now I have this Y data, which is the best fit data, Y best fit data. So this Y best fit data, the Y best fit data is now generated. Okay? So what I'm going to do is I'm going to plot the functions of X data and Y best fit data. So this will give me the functions, a continuous function. It looks like this, right? So this data, let me put in a red color with a double dot. Right? So this double dot red function is the one that is generated from this function f, and this is the plot data, which is the original data. Okay, so both of them, when they combine, then you see this. So I have all these data points, and then I also have a function that is being described like this. Okay, but the Y data here is not smooth because I'm only using the X that is in X data. So this X data has only 6 points. But in principle, I can make the functions of Y data to be finer, to be a bit more fine. For example, just show you how I do it. I'm going to modify this. And what I'm going to modify is I'm going to make the X data to be more refined. Then I'll ask the Python code to generate a function where the X is separated more fine. Okay, so this X data, I'm going to replace it by something else. I'll call this X, whatever, just XP, MP dot arrange. Then I'll start off from what? So here, I start off from X data is from 0 to 5. So I'm going to start it from 0 and add 5, but I'm going to make it 0.05, for example. So this XP data will be 0, 1, 2, 3, 4, 5, but much finer than compared to the original data. So this XP data, I just replace it into XP here. Then this X goes in the function will be evaluated for many times. Then I'm going to plot XP data. So when I press button, this will give me a function which is going to be represented by the dotted red color line, but it will be much smoother. So this function will be plotted not only with 5 points, but many more points. Then this function that's fitted will be overlapped with the data point that's originally there. So this function is smoother than the previous one because now I'm replacing this function f with a much finer data point, which is like this. Okay, so that's how we did the thing, right? So this is basically what I do in this case. So here I find the functions, and then I extract the best fit values of A, B, and C. Then I plot it. Okay, so I plot the function and it's like that. But here, the function that's plotted blue color line is sort of like not continuous because it's not using a lot of data point. But here, I'm using a much more smoother data point by using X data, which is XP, right? So it's like maybe about 100 data points instead of just 5 data points. Right? So I think you get here is that I give you a set of data, then you try to find me the best fit parameter, then you would overlap the best fit parameter, the best fit function on top of the parameter. And then if your fine fitting is best and is done properly, then you see the function that goes like this or like this, either way. Okay. So it's very easy to do the fitting. So next time, example, if I give you a set of data that looks like this, are you able to fit the functions? Yes, of course you can. If I give you this data point, can you find me what is the best fit values of A1, A2, A3, and A4? Of course, yes. So I'm going to make this as an assignment to you. So it will be a simple assignment. Some data point given to you, a function is given to you, and your job is to find out the best fit parameter for this data point as well as for a linear data point. Then your job is to find me the best fit parameters. Once you have found it, then you have to overlap the data point onto a function that's been fitted. Okay, so that is the idea of what we call a curve fitting. Okay. So that is what I want to tell you for the moment. Any feedback from the audience would be much appreciated. Basically, what we have learned in this curve fitting is what you do in your second year lab and first year lab. So in your lab, you have this straight line, right? So we try to find out what is the best values of the slope and the intercept with the data point. Right? So you can do this very easily with Python using the curve fitting function I have just shown you. So remember this function, SciPy dot optimize dot curve fit. So you have learned in this afternoon the function called curve fit. Okay, provide the form of the functions, the data point, and then define your function in this manner. X is a variable. Sorry, it's an independent variable. A, B, C are the parameters to be fitted. Then you define your function. Okay, so make sure that you make a distinction between the parameter to be fitted as well as the independent parameter. So in this case, X is different from ABC, okay? X here refers to the X data, whereas the ABC is the parameter to be fitted in your formula. So next, we are going to go to the next example of another situation, which is kind of easy, but it's about taking the average of experimental data point. So this is a very simple situations where you have a relationship that relates between the height of a ball and the time taken for the ball to bounce, right? So not the bounce, I think if you know the ball was dropped from 6 times from 1 meter. So what you do is that you take a ball and you put it at 1 meter height from the ground, then you release it. Then you measure the time for the ball to fall through 1 meter when it hits the bottom. Right? So you do this for 6 times. So this is experiments that you did when you was in Form 1. Right? So you take 1 meter, drop the ball, assume the ball suffers no impact force. Then you measure how many times, what is the time taken for this to drop. So this is an experiment, which is like 0.14, 0.714, 0.69, 0.61. So these are the numbers that represents the seconds that you measure when you drop the ball for 1 meter. Okay, so you know the relationship between the height that is dropped through by the ball under gravity and the time, right? So using this set of 6 measured value, you in principle will be able to calculate the average values of the graph. So there are many ways how you can do this. Now, one way to do this is to use optimize function that are being mentioned just now. So we're going to do this by using SciSpy optimize curve fit, right? So in this case, we are going to fit sort of like the function of t against h, and you put in the data of t and h. So here you are carry out 6 independent experiments. So you set the h, then you measure the t. You set the h again, you measure the t. So you do this for 1, 2, 3, 4, 5, 6 times. So the first time you set h equals to 1, you drop the ball and you measure 0.814 seconds. And the second time you set the h again to 0.741, then you measure the data again, the time again. So you do this for many times, and then you record different numbers of time when it drops. Okay, so you have to distinguish between 2 sets of data. One set of data you call the X data, the other one you call the Y data. So the X data is usually the data that you can control. So in this case, the X data is the height, which is 11111. And the corresponding Y data is T. T1 is 0.81, 0.74, 0.9, 0.69, and 2.75. So there is a very simple formula that relates the functions of T, the time measure, and the height that you drop is simply given by this formula, that is T equals to square root of 2h times G. So in this case, you have different values of T and you have different values of h, right? So you can treat this h as your X data, you can treat the T as the Y data. Then your job is to try to find out what is the best value for G. Okay, so this could be easily done using the functions of the optimized sci-fit. So let us try to reproduce the graph here. Try to go through this exercise again. I have to cut out this one. SciSpy optimize curve fit data. So this is what I want to do. Okay, well, let's go to this very fast. So my experiment here, T versus G, and this is okay, let me yeah. So this is a function I'm going to use later. SciSpy later. Okay, so I'm going to create my X data. My X data is actually the H data. Right? The H data is taken to be 1.0, 1.0. So how many data? So this is my T data. So there are numbers of 1, 2, 3, 4, 5, 6. So the T data here corresponds to the X coordinate. Here should be 1 meter. So there will be numbers of h1 meter. What do you call 1, 2, 3, 4, 5, 6. So there will be 6 h. So I think I can do this. I'm not sure, but let me try. So if I do that, do I get any error? Print out h data. H data should be, yeah. So this is my h data, and then define correctly. So I have the h data has been defined and Y data has been defined. And in order to fit the data to the function, I have to define my function to fit. So what is my function to fit? So define my function to fit. So the function to fit is this, right? Add T as a function of H. Okay, so the Y, the X, the T is a function which is equal to square root of 2H over G. So function here is T equals to 2 times H over G. 2 times H over G. And so this is what is going to be returned. return t equals to 2 times h over g. So I have to tell the function. The function should admit two variables. One variable is the independent variable, which is the h, which is the y, the x values that is going to be taken from h. And then g is the parameter I want to optimize. Okay, so this is the independent variable. This is the function to optimize, and this is nothing but just the t. Maybe I should call this t equals to this, and then just say return t. I think that would be maybe better. So if we find t and then I return t. Okay, so that should be correct, right? If I'm so I'm not sure. I always not very sure about my functions. So what I do is that I want to print out the values of say h equals to 1.0, g is say 7.0. So I expect when I press a button, I should get some number. Yeah, I get some number. That means my function has been defined correctly. So now I'm ready to go. So I'm going to use the science by optimize curve fit to fit on this function. And then this is my x data. My x data is nothing but just the h data. And then the y is my the y data is my t data. Okay, so I have to be very careful because I am calling this a h, and here I'm calling this h data. So I'm not very sure whether this is correct. Okay, now I'll press the button and see what happens. Okay, so I get two numbers. This is the number I got 2.7. Then this is an array. This is actually the array matrix, which is containing the error of this specific parameter. So it says that the g that I obtained is 2.7. So I was wrong because this is supposed to be a square root of 2. So I forgot about the square root of 2. So this should be square root of 2, which I should include it. Square root of 2, okay, that should be the way. Okay. So let me press button again. So the answer I get is sorry, not 2, 0.5, 3.81. So this is the values for the best fit parameter for h. Okay, so if I'm not mistaken, this is the values of g. Okay, so h data here refer to this h, whereas g is the parameter that goes into here. H data and g data. Okay, so that means this is the output. The result is output. So the output is this. Then the output number 1, the first element in output, which is output 0, which is 3.8. This is 3.87. So this is the output. So my result is this. So there is an error. Well, there's this thing here means that the error is actually not an error. The output is an array. So I just want to extract the array. So maybe it's 0, 0. No, right? So it's 0, 0 like this. So that's how I extract the values from output. See, the output is an array. The first element in the array is the best fit values for G. The second element is the error, and I don't want the error. I just want the best fit values. So that is how I get the best fit values of G, which is equal to this. So here, the optimized curve gives me the best fit values of G to be 3.813. So which is not very beautiful because we know the general values for the G is actually 9.81, right? So it's 3.83. But this is the result that we got from the data. So the data is set at h equals to 1. And then this is a t taken. So is this the correct value? So probably it is. Now, how do you know that it is? So maybe we can take a look at this side. So if you look at h equals to half gt squared, and you make some small rearrangement, you find that you can express the g equals to 2h over t squared, right? So 2h over t squared gives you a rough idea of g. So let me, what I'm going to do now is I'm going to check whether these values of 3.81 is consistent with the values that I expect. So g, according to the formula there, is 2h, 2 times h over t, right? So the output from give me 3.81. So it means that if I were to sort in h equals to 1, 1.0, and then divide it by the values of t. T is, so I should see a number which is roughly equal to 2.81. So let's see if this can be printed out. No, it can't be printed out like this, but I'm going to print out the values of t, right, for t in t data. So this way will print out 2h over t for t in t data. So this is an array that lists out the corresponding values of g for each t. Right? So when t is the first value, this is what the g formula predicts. So you look at here is 2 point something, 2 point something, 2 point something, 3 point something. So that means that the formula, if you use this formula and slot in the t data, then the values of g would fluctuate around 2.8, 2.9. So this number of 3.8 something seems to be quite agreeable. We have a very large values of 3 here. So the answer is correct in the sense that it is calculated based on the data. So maybe it's the data in the experiment that is lousy. Therefore, you've got the values of g, which is much different than 3.81 because the values of t measured is lousy in a sense. Maybe there's some error in the example. Maybe what you should do is that usually what you do is that you would measure the time for different height. So instead of a height exactly 1 meter, perhaps you should drop it from different height. Then you have a h to not fixed at 1, but h would be like 1.0, 1.2, 1.3, 1.4, etc. Then you measure the time taken to fall for different h, then you get the values of g. But anyway, we are not really care about the values of g calculated from here. What we are here is how to use the optimized SciSpi, the optimized function in the SciSpi to get us the best values of g given the formula. Okay, so these are the simple example. So I'm going to leave this example, the rest of the example for you to ponder. So this example, last example, you can slot in an error that would sort of like improve your calculation of it. I'm going to discuss it here. So if you're interested, you can try to read it for yourself. Okay? So that's how we have shown you two very simple examples of how to use SciSpi optimal curve to fit a function. So later on, when we come to the assignment tonight, I'm going to define the assignment. I'm going to give you 3 functions. I'm going to give you a function for an XY plot. So your job is to find me the best values of M and C. I'm going to give you another example of data point for a Gaussian function. You're going to find me what is the best values of A and B. And later on, I want to plot these functions. I'm going to give you this data point. Then you download this, you import these data points into your Python code. Then you define a functions that will allow you to print out A0, A1, A2, A3, A4, and then you overlap the functions using the best fit values of the parameter and overlap it onto the data point. So that is going to be your assignment. It should be very simple. You can actually ask me any question if you are doubt. Okay. Let me see, still people are still there. So I still see numbers of you. No questions from you? None of you will have questions to ask? Now I have decided that maybe I should not teach too much, or else people would be very bored, and then maybe we should not be too ambitious. So today we're going to not stop here, we will take a rest here. Then we're going to go to the next part, which is on the part 6, right? So you can go to the part 6 of your Python notebook. So here I think you can go to the part 6. Press a button in your furniture, then you'll be brought to part 6 IP1. Why is it not there? What is this? This is not converted. Let me check. I'll just schedule the attendance first. Okay, take a break. Then we come back at 4:10. At 4:10, we continue the second part of this lecture. Should be quite fast. So switch on the camera for those who have not. So we'll see you at the 4:10. I'll give you a break of 6 minutes. Okay, it's 4:10. Try to make this a bit short. So we're going to go to Python, the part 6. Now, the part 6, we're going to go to half of the part 6 today. I think the last part, I think there's some problem with this. So we're going to fix this part, solve a differential equation or coupled equations with two variables. I think it doesn't work very well. So I have to fix this. So we're not going to talk about this today. So maybe in the next sessions. Hope that you are ready. I'm going to continue with this part 6. So you can click on the part 6. We're going to solve numerical equations with SciSpy. So in this example, we are going to solve for the roots. Okay, let me switch on my part 6. So solving equation numerically with SciSpy, part 6. So basically, this is the part. Okay. Now, what I'm going to do here is this. Usually, if you have a function, right? So you have a polynomial, for example, and then you want to know what is the root of a polynomial. So basically, you can easily do that. Functions of polynomial is described in this form. So the most important thing when you talk about a polynomial function is that you have to know what is the order. The order is n. So a polynomial of order n has the largest powers of x of n. And then the lowest term is a linear term. Well, it's a constant term, C0. And the second term is a first order term, second order term up to the n order term. Okay, so this is a polynomial. You have to recall your ZCE 110. Most of the time, we have to recall we have to recall the knowledge that you have learned in your 110. So given a polynomials and given a x low limit and x upper limit, we want to know what is the values of the polynomial. How do you do that? It's very easy. You can find out the roots of a polynomial for any order using a very simple functions called size by roots. So what you need to do is that you just have to provide an argument to the size pi root functions. What is this argument? This argument is just an array that describes the coefficients in a polynomial. Right? So for a polynomial of order n, it has coefficients of Cn, Cn minus 1, Cn minus 2, up to Cn, C1 and C0. So you have to provide the coefficients to the size pi roots, where this argument is an array that contains all the values of Cn. So how many Cn are there? So the numbers of Cn that should go into the array of a polynomial is just the length of the array. You do not need to say, okay, and there are five coefficients, there are 8 coefficients. You don't need to say that, but you just enter the values of the C one by one into the array. If there are 8 entries, that means the C is the C has up to n equals to 7. If you slot in, say, array of say 3 to 1, means it is an polynomial of order 2, right? So the numbers that goes into the array is the numbers of the coefficients. Okay, so for example, if you have a coefficients of a function of say polynomials of order 5, so a function of polynomial order 5 have C5 times x power 5, C4 x power 4, and this should be C3 times x power 3 plus C2. So this is an example of a polynomial of order 5. Now, in order to find the root for this polynomial, you have to supply the coefficients. So the coefficient should go into the array. So the first entry here should be the array of C5. So this is the C5 array, the value of C5, C4, and then this should be the C3, and this is the C2, this is the C1, and this is the C0. So in this case, if you have a functions of say like this, x power 5 minus 1 plus 5, this is a polynomial of order 5, where the coefficient C5 is 1. Coefficient for x power 4 is 0. Coefficient for x power 3 is 0. Coefficient for x power 2 is 0. Coefficient for x power 1 is minus 1. And the coefficient for C0 is just 1. So the correct way to translate this coefficient, this polynomial, into the set of coefficient array is very easy. So you have to specify, since this is an order 5, so that means you have to have 1, 2, 3, 4, 5, 6 number in the array. The first one is the value for the largest coefficient, and the last one is the coefficient for the constant, right? So here the C1 will take on the value of 1, C4 is 0, C3 would be 0. C2, which is the coefficient for x power 2, is also 0. But the coefficient for x power 1 is minus 1. Right? The coefficient constant is just 1. Okay? So that is how you derive your coefficient. You call ARR. So when you say this ARR equals to this, and you put this ARR into the root function here, like here. Then it will automatically find you the roots for this from scratch. So let me try to find a function for this. So this is a call. So what I'm doing now here is that I'm looking at the solution for the functions of x power 5. So my functions that I'm going to solve for is a function EES. I call it the functions. The functions would emit values of x, okay? And then in return this, okay? So this function would be an argument of ARR. Let me see. ARR, maybe it's not fx return. Yeah, so I just simply have to explain that this is a function I'm going to fit. And then I have to define the functions. Well, what I'm saying is that the ARR and the function I define in the function f is has to retaliate each other. Okay? So so this is how I define my ARR. And then the next thing I want to do is that I have to first import numpy, and then I have to import what else? I have to import SciSpy as well. Import SciSpy. Import numpy and import SciSpy. I have to import from SciSpy. I have to import optimize. So I need optimize. I need SciSpy, and I also want to use the fit functions, which is called the SciSpy roots. Okay, so this is what I'm going to use later on. SciSpy root. Okay, so at this stage I have done nothing. I just define the function. I just define the array. So now I'm going to use SciSpy to find me the roots for the polynomials which I define in F. Okay. So what is the coefficients? The coefficient is ARR. Okay. Now, even though I do not have this, even I do not define my functions, but this ARR, which contain the coefficients, actually represents in another way this function. So I'm going to use the function fx later to plot the functions, whereas the array ARR that I define here is to be fed into this SciSpy in order to obtain the roots. Okay. So later on, I'm going to plot the function fx together with the roots and see whether the roots is indeed lying at the zeros of the function. So before I carry out all this, so first of all, I always want to plot the functions so that I can visualize it. So how do I plot the functions? I will say plot. In order to plot the function, I need an numpy. I need to let import everything. Right. So let me plot the functions. This is always what I do. I plot the function of x data and x data. X data should be an array, right? It should be an array of a range that will give me from x, well, f1, x2 with n delta x. Okay, I'll call this x data. X data will be this. Okay. But what is my x1? X1 is the values of the x I want to plot from the left. Is it in the right? So let me call x1 equals to say -1, just an example. X2 equals to 1 example. And then delta x is just the difference between x2 minus x1 divided by some discrete number, say nx. So I'll just say, okay, nx is to be discretized into, say, 10 number. So when I press the button, I want to see an X data will be printed up, and it should be an array. So yeah, not so I should paste this. So I don't see array X data. Where is the error? Error is I has no attribute. So I will time is empty import I let everything. And then I also have to just cut and paste. Import my file as empty and blah blah blah. Empty size file will be not size file. So error again, numpy has no. Okay, so I think there's this error. Ring. Okay. Yeah. So there's a mistake in the study. Okay, so X data is this number. So now I have successfully generated X data using NP arrange. So now I'm ready to plot X data and F data. So you just have to specify X data and F data. I think that should allow you to plot the functions. So this is a function that I have defined. It's starting from -1 to 1, but it doesn't go through at 0, right? So it's not a function in this range from -1 to 1, it doesn't go through. So maybe I should make x1 to be, say, -5, x2 to be 5, and then maybe I should make this to be larger, maybe 50, so that I can see the function better. Okay, so now it is not looking better. It's -50 to what? Okay, so this is an error. This should be 5, and this should be 5. Yeah, so I should not print out this text. Okay, so now you see these functions. So you see that they should go through 0 somewhere here. So there's a 0 that is between, like, maybe somewhere here. So maybe I should just restrict from -2 to 2. So I change my x2 from 2 to 2. Then the function will be more clear. So I expect an error and a function will cut through the 0 somewhere around this area. So I do not know exactly whether would there be a single root or would there be a double root. It doesn't matter. So I have plotted this one. So now I'm going to find the roots. So the array ARR 1 0 0 0 -1 0 represents this function. Okay, represent this polynomial of the 3. So when I press a button, this is the root I'm going to see. So I'm going to see this. Print out the roots. Before I plot the functions, I print out the root first. Right. So now you see this is a polynomial of order 5. And you have 1, 2, 3, 4, 5. 5 roots. Out of this polynomial of 5 roots, only the 0, 1 is a real root. The rest are all imaginary roots. Okay, so just to remind you, a polynomial of order n has n roots. For example, y equals to mx plus c is a polynomial of order 1. Therefore, it has 1 root, like a straight line goes through only 1, 0. If it's a quadratic functions, then the maximum roots you have is 2. Right? Quadratic function is a polynomial of order 2. So this is what I expect. I use the size pi arguments of the coefficient, then I have all the roots. Right? And out of these roots, this is the roots that is real. The rest of the 5 roots are complex. Okay, so now I have the roots. So let me extract the first roots. The first root is this. Right? So this will give me root but the first root is still inside an array. So I'm going to call out another 0 just to get rid of this. Okay. No, 0, 0. No, can't get it. So the roots is still this. Okay, doesn't matter. So now I have a functions. I have the roots. So let me plot the roots. Now this is the x coordinate of the roots, and then I'm going to evaluate the function at the roots. So by doing that, this particular line will print out a dot, and the dot I will make it to be a red color dot with an asterisk. So when I press a button, these two plots will be merged together to place a dot onto here, which is the roots. Okay. And at the same time also, I have to see what is the values of the function at the root. So this is what I'm going to see. I'm going to print out the values of the functions at the root as well as the values of the roots. And I expect that this should be a number which is very close to 0. Like by definition, a root is a function, is the values of the function where it is close to 0. Okay, so this is what I expect: a 0 value for the function evaluated at roots, and a line, and then also the coordinates of the roots. So we got some warning, because this is not exactly pure. It has a component which is 0 in the complex plane, but it doesn't matter because it's 0. The 0 here refers to the complex plane. So this is a number which is extremely small. Right? So this is where the root lies. And the polynomial that looks like this is very nice. Right? So now it's a very simple exercise. You can now calculate the roots of any polynomial for any function you want. Okay, so this is very easily done. So now let's just try to another example. Let us try to look at an example which is like a polynomial of x power 2, say minus x plus 1. Okay, so let us try to make the changes to this. Maybe this is maybe we change it to minus 9 in this example. Okay, so we have a polynomial of say x power 2 minus x minus 19. So in this case, the coefficients array will be different, right? So this should be the powers for, maybe I will use to be say 4x squared minus x minus 9. So in that case, the first coefficient will be 4. Then the second coefficient will be minus 1. Refers to the coefficient to the x term. The last term is 19 minus 19. Right? So this would be the coefficient that represents the coefficients. So let's just try to see if I can print this correctly and plot it out. So it's the functions, and then the 0 is here. Right? So the functions cannot. Well, the function has zeros at somewhere here, at somewhere here. So the zeros lie not at between minus 2 and 2, but is on the left of minus 2 and on the right of minus 2. So I should plot the function, say from minus 3 to 3, to display the functions more holistically. So now you see these two functions. It is this one, and then there's another function here. So this is the roots, the second root. So here I only print out the first root and the second root. Now I should also print out, if I want to, I should also print out, say, roots number 1 and number 1. So this would be the second root. So if I do like that, now maybe I should just show you one example, one panel. Now the output of these roots, ROTS, which is the result from size find, should contain two roots. Right? Should contain two numbers. So this is the first root. The second is what is being plotted here, and this root should be the roots which has an index of 1. So I will, if I do like this, I'm going to print out this root, print out root number 1 as well, and then evaluate the values of the function. So this will give me the values of the 0 root and the first root. So it will plot 1 point for the first root and the second root. Then you plot all these 3 functions together, give me 2 points and 2 roots. A 2 point representing 2 roots and a function. So it should be quite clear, right? So any polynomials could be easily obtained for its roots. So if you have a polynomial of, I'll say, power 5, power 3, power 2, as long as the roots has a real value, it could be then found and be printed out on the screen. So next time I give you a polynomial, I say, okay, try to find me all the roots in the polynomial, and you should be able to do it. Right? So just go through this exercise. It should be quite simple. But then there will be some problem. How about if you have a function which is not polynomial? That will be difficult. Now, just to remind you before I leave this part, the size pi, this function, this function that we are using, the roots function that we use here is only meant for polynomial. Now, if it's not a polynomial, say for example, some transcendental function, for those who still remember what you have learned in your ZCE 110, we learned about many different types of functions. One type of functions that is most common is the polynomial functions. But they are also transcendental functions, for example, hyperbolic function, tangential function, trigonometric function. So for this function, you may not be able to find the roots in this transcendental function using the size pi roots. So you have to use some other function. So there are basically 2 types of function in size pi that you can use to help you to locate the roots. Other than ROT for polynomials, there's another function which we call fsolve. So fsolve is another function that could be used in size pi to obtain the roots for function which is not polynomial. Okay, so this is what we're going to talk about the next couple of minutes before we end today's lecture. So it's very easy. But the difference between the fsolve is slightly different than the roots. So in the roots, find that. Let me show you the roots. Okay. So if you look at the roots, what you need to do is just to tell the roots what are the coefficients of your polynomial. Okay. If you are going to use the other function, which is fsolve, to solve for the roots of the function, not only you have to provide the function through the fsolve, you also have to provide the guess for where the root should be located. So not only you provide the functions, but you also have to provide the location, the initial guess. Okay, so x0 is the initial guess. So let us now try to look at an example how you use fsolve to solve for a function. Okay, so in this case, you have to provide the function as a whole to fsolve instead of providing the ARR or the argument for the coefficients like what you did in the roots. Okay, maybe I just do like this. So in order to use the fsolve, you need to import optimize. So optimize is a function that is found in size pi that is going to be used to find us the best fit parameter, or to find us the coefficients. So in this case, let us look at again the example of the function that we're going to find its roots. So we can use the polynomial. We can use other functions, say for example tangent function or x times tangent function. We'll do it later on. But let us use the polynomial x power 5 minus x plus 1 as an example and show you how you do the root finding. So my function, I think I can try it out. Do this all over again from here. Hopefully that I will not encounter too much error. Okay, so let me see if this is okay. I don't import SciSpy. Okay, fine. So this is okay. So I need to import SciSpy and I need to import optimize. So I don't need to do this. So I have defined my function. So now what I need to do is I want to find the roots for this function polynomial x power 5 minus x plus 1. So I have to use SciSpy. I call this SciSpy optimize. So you call up SciSpy, you use the optimize object from SciSpy, and inside optimize object, there's this thing called FSOLVD. Right? So this is the SciSpy fsolve. Now, how do you use SciSpy fsolve? Now, one way to tell is to ask for the help. I think you can try to learn how to use the help. Yeah, so this is a help file for how to use SciSpy optimize solve. So you don't really need to memorize all the syntax. Anytime you don't remember, you can just type in and just provide this. So this is how you use the syntax of SciSpy. Right? So it says, provide me with the function. Then tell me what is the initial guess. Then the rest of this, you can just use, you just set it as a default. You don't need to do anything, just set it as a default. So you need to define the function, and then you need to define the variables of x0. So that is what I need to do. So fsolve, then you have to provide the argument. So this is f. And then you have to provide what is your initial guess. So I call this x0. So you have to provide initial guess and say the initial guess is provided at 0 and see what it gave us. So if I do it correctly, x0, if I do it correctly, when I press the button, this would try to obtain from me the functions of x0. So, but before I always, like I said, I always want to plot the functions of f. And then x, the x is the data, which is for x. So I have to generate the x data. Well, this is x range, which is np dot x. So this is x data. So the x data x data x, yeah, x and x data. So x is the functions of x data is just np dot range of say minus 2 to 2 with 0.1 as intervals, and then this is x. Not sure whether this will work. Let's try this. Yeah, it doesn't work. Of the range. Get to work. X data. Yes. Yep. So it works. So this is my x data. Yeah, it goes from minus 2 to 2. So the roots is somewhere here. So maybe between minus 1.5 and 1.5. So it looks like there are some roots between here. So let me try to make a guess for the roots by assuming that the roots is sitting somewhere at 0. Okay, so this is my guess. Now when I press a button, the SciSpy optimize fsolve will try to find me the closest to 0. Okay, if there are 2 roots, then maybe it could only find one, but it would not find many. So let me press button. So you get, yes, there is a root which is 0.06. So somewhere 0.66, somewhere here 0.66, there is a root. Okay, so this is the first root. Give me some warning, but still you get the answer there. Now what happens if you begin your guess not from 0, but say start from say minus 0.5. So if you start from minus 0.5, starting from here, then the search algorithm will try to go along this line and try to see if there's any root that is closer to here. So there could be 2 roots. So which root is closest to your initial guess will be found first. If there's only one root, so that means no matter where you start from, you always end up with the same root. So now let's just remember, if you start off from 0, 0, you get this. But what happens if you start from not 0, 0, say minus 0. So let me see here, let me minus 0.5. Do I land on the same roots? Should plot. I should print out this one. I should print this. When I change the initial guess, the result should be different. Yes. See, if I use 0.0, the roots is this 0.6868. If I use x naught equals to minus 0.5, then I land on minus 1 point something. So this is my roots. I call this R1. I call this R2. Okay. So once I have found R1 and R2, then I'm going to plot my function again. I'm going to plot my functions over again, but this time I'm going to make my arrange starting from R1, and then I'll do it and then I'm going to make R to be slightly, the X to start from slightly less than R1, say by 0.5, maybe 0.25, and end at R2 at 0.25, so that when I plot the functions, plotted sort of like slightly left than the first root and slightly right than the right root, so that the function could be plotted in such a way that I can see two roots very clearly towards near to the end. So then I plot this. Okay. So what happened? R1 and R2. Okay, so I think R1 is not defined properly because R is not the type. Okay, so let me see what happened. Because this is R, so R seems to be fix it up. Okay. So I want to see what is my X data. My X data here. So let me check my R2. R2, R1, R1. No, so it should not be R1. It should not be print. It should be just R1. Should be just like this. R2 should be just like this. So it should not be a print. So I think that will work. Yeah. This R1 and R2 plotted, and I'm going to print plot not only this. I'm going to also plot and also plot the values of R1 and F at R1, and then I'm going to plot also R2, F at R2, and this will be a red color star. And also I'm going to print it as a red color star. Okay, yeah, so I see two roots here, 1 and 2, right? But right that the roots of R1 and R2 are calculated sort of like manually by changing the initial guess. This is unlike the solve, right? In the solve, where you solve for the roots of the polynomial, one shot, it will solve you all the roots if there are many, right? So you don't need to specify the initial guess, but the roots, if there are 5, it will give you 5. If there are 2, it will give you 2 automatically. But in the F solve, you have to guess, well, the board initial guess. One initial guess will end up with one root. So you do not know, if you do not know how many roots are there in your functions, then you have to think of the clever way. Right? So you have to scan, say x0 is like minus 3. Then you try to find what's the root. Then you set x0 equals to say plus 44. You guess again and see whether you got the same answer or not. So that will be a challenge to you. Now in my assignment, I will try to do this. I'll try to ask you to find the roots of a function of a single root. So if you have a function, for example, a tangent function, which is limited to between, say, minus pi to pi, and you know that there's only one root. So you can use fsolve to find that single root. But what happens if you have a function and you have two roots, how are you going to automatically assign an initial guess and then get the roots? Now, in the worst case is that you are given a function and you do not know at all how many roots are there. There could be 2, there could be 3, there could be 5. So in that situation, you have to think, can you invent a code, Python code, that could automatically scan the range into intervals? Intervals, you pick an initial guess, then you put the initial guess into the fsolve and see whether that fsolve gives you the correct answer or not. Well, if there are more than one roots, when you scan through the x value, you would get different output when the initial guess is taken from different intervals. Now, this is a challenge, okay? It could not be very easy, but it could be done. So I'm going to give you a function, say, I don't know what function, I think about it, but I will not tell you how many roots are there in the function. Now, the challenge is that, can you develop a code that when you press the button, it will automatically find out all the roots for that. If there are 3, it will find out 3 roots. If there are 5, it will automatically find out 5 roots. And you are not supposed to tune the input values of roots manually. Now, in our case, I have to change the function, the input value x0 from 0.0 to x0 to 0. minus 0.5 in order to get different roots, right? So if there are the third roots, which is located at, say, near to, say, initial guess at, say, x equals to, say, 45, then how would you locate the x45, right? So within some limit of x1, x2, locate numbers of roots and then print out the distinct roots for me automatically without human intervention. Okay, so that is a challenge. I'm going to set the very simple tutorial question for you tonight. Maybe you have something to do during the weekend. Okay, so maybe that's all for today. If you have any questions, you can ask now. Anyone? Okay, everyone is quiet. But anyway, we have gone through a few exercises. I think we are sort of like getting into the mood of running the code online. So I have saved this session. I'm going to upload the recorded sessions to the e-learning as well. The session that we did in the last lecture, I have not recorded it properly, so I'm not going to put it up. But for all those recorded lectures like this one, which I have a full set of recording for 2 hours, I'll upload that so that anyone who have missed it out could submit the assignment. So I'm going to set the assignment maybe 1 week instead of a few days, so I have more time to do assignment. Okay, so that should be fine. Any one of you who have problem, please contact me. You can contact me through the WhatsApp group or any means. Now, if you have friends who have problem accessing the internet, the real-time internet, you can look at the recorded video. Like, for example, this recorded video will be uploaded, but for the past 2 ones that we have not recorded, that I'm not going to upload it. But beginning from this session onwards, please remind me in case I forgot to press the record button, then I will not be able to record this. But today, I think I have recorded the whole 2-hour sessions. So I urge you to remind me in case you find that I have not recorded the session, please remind me to do so. Then after that, I'll upload this recorded video to the link. Then everyone can look at it, including those who have missed the online lecture. Okay. So if there's no problem, I'll end my lecture here. Any problem, just let me know lah through the WhatsApp group. Okay. No response. Okay, fine. Sejak Mariam.
Doktor.
Ya, boleh cakap. Okay, it's okay lah. So no one will say anything. So I'll see you again next week. That's all. Sure.